So tonight we have Dr. Ekta Patel with us. So Dr. Patel is a Miller Fellow in the Department of Astronomy at the University of California, Berkeley. She received her BA in physics from New York University in 2014 and her PhD in astronomy and astrophysics from the University of Arizona in 2009. At the U of A Stewart Observatory, she worked to analyze computer simulations that help us understand the dynamical history of the local group. At UCB, she's working to understand the dynamics of satellite galaxies orbiting the Milky Way and Andromeda. She's specifically interested in individual orbital histories of these galaxies and how the collective phase space information of these systems of satellite galaxies can reveal important properties of their host galaxies. So without further ado, Ekta, you can take it away.
All right, can you see those slides?
I can see them on my end, but there's a delay between YouTube and Zoom. So why don't we wait like 10 seconds just to make sure that it shows up on the stream. It should be good though. Yeah, looks good.
Okay, thanks for that introduction, and thanks all for joining me today. I know we're living in this strange new virtual reality, so I'm grateful that you've chosen to tune in for this talk. So I'll be talking about satellite galaxies in the local group. And so for the first few minutes of my talk, I will just dissect that title and talk about satellite galaxies and what I mean when I say the local group. And I'll also come back to this image on the title slide. So the goals for this talk are to explain to you what are satellite galaxies and why are they important. And then in the second half of my talk, I'll be giving you some details about how astronomers use both observational data as well as computer simulations to study satellite galaxies. So first, before I dive into what satellite galaxies are and why exactly they're important, I want to spend a little bit of time defining what I mean when I say galaxy. So typically when you hear the word galaxy, you might think of an image like the one in the background that I'm showing here. But this wasn't actually always the case. And in fact, even in our modern definition of a galaxy, which is still changing, it's important to continuously redefine what we mean when we say galaxy, given that our knowledge of astronomical objects is changing on a pretty rapid basis. So what do I mean by a modern galaxy? You likely think of images like these that I'm showing here. All of these beautiful different morphologies, different colors, different structures in these galaxies. But the question is, why aren't these objects classified as galaxies as well? And the reason why this definition is changing is because we're discovering more and more objects in the universe that are very faint and that have a broad diversity of properties. And so that modern picture has to change to keep up with it. And it was actually only about 100 years ago that there was something called the Great Debate, where two academics argued against one another about whether our own Milky Way galaxy was then the entirety of the known universe, or if it was just one galaxy, which was then called spiral nebulae, amongst a sea of many. So even now, this definition is still being updated. And just back in 2012, a couple of astronomers took to writing down what we actually mean when we call something a galaxy these days. And this is what the modern definition is. A galaxy is a gravitationally bound collection of stars whose properties cannot be explained by a combination of baryons and Newton's laws of gravity. So that's quite a mouthful, so let's break this down a little bit further. So when I say baryons, I'm talking about subatomic particles like protons and neutrons. And when we talk about Newton's laws of gravity, we're talking about the basic laws of gravity you might have learned if you took a high school physics course or a college physics course, where we say force equals mass times acceleration, and that massive bodies feel equal and opposite forces, things like that, the basic laws of gravity that we see around us every day. But what does that mean in the context of galaxies and the pictures that I was showing you just a slide ago? What that means is that galaxies must have some additional mass, perhaps in the form of something called dark matter, to explain what we now see as a gravitationally bound collection of stars. So going back to the definition of satellite galaxy, we now know what we mean when we say galaxy in particular, but let's look a little bit more at satellite galaxies and why I've spent so many years studying them and why my collaborators and I are still interested in looking at these. So a satellite galaxy, just like the moon orbits around the Earth and moons of other planets orbit around those planets, is a galaxy that orbits around another galaxy. In the context that I'm talking about today, Satellite galaxies are typically orbiting around more massive galaxies and significantly more massive in that the host galaxies that they're orbiting around are at least 10 times more massive than the satellite galaxy, if not much, much more massive. And now let's go to the local group. So my title was Satellite Galaxies in the Local Group. So what do I mean when I talk about the local group? Well, in the most basic of senses, we're talking about our own Milky Way galaxy and the dozens of satellite galaxies that we know to be orbiting around the Milky Way. In addition to that, we also have our nearest, most massive spiral galaxy neighbor, the Andromeda Galaxy, that also has its own population of dozens of satellite galaxies that are orbiting around it. And the final third sort of subgroup of galaxies that we typically find in the local group are isolated dwarf galaxies, like the ones I'm showing in the bottom left here. These isolated dwarf galaxies tend to be fairly low in mass compared to galaxies like Andromeda and the Milky Way. And they don't really appear to be gravitationally bound to either of these larger systems. Nevertheless, we consider them as members of the local group, which in radius is approximately 3 million light years across. And these two main members, the Milky Way and Andromeda, are also separated by roughly the same amount, about 2.5 million light years across. But this graphic is actually only showing you a subset of the galaxies that we know to be orbiting around both the Milky Way and the Andromeda Galaxy. And in fact, it wasn't until really the last 20 years that many of these satellite galaxies came to be known to us. Because they are so faint and low in mass, they're actually fairly difficult to discover. So if I briefly show you the timeline, the discovery timeline of satellite galaxies around the Milky Way, this is what we're talking about. So on the x-axis here, I'm showing the year of discovery, and this goes back to the year 1700. And on the y-axis, I'm just showing you the number of satellite galaxies we've known of as a function of time. So the first two satellite galaxies that were discovered around the Milky Way are the Large and Small Magellanic Clouds. And while this timeline only goes back to the year 1700 for convenience here, the Magellanic Clouds have actually been known to humans all across the southern hemisphere, where you can see them in a very dark region with just your eyes, for many, many hundreds of years. So if we look at the Large and Small Magellanic Cloud, here's what they look like on the sky from the ground. And they are the two most massive satellite galaxies that we know to be orbiting around our own galaxy, the Milky Way. If we go back to this discovery timeline, we of course know of many more satellite galaxies these days. So between the year 1950 and the year 2000, there was this large increase in the number of known satellite galaxies that were discovered. And these are these were largely found in photographic plates, which means that this was before the advent of the fancy telescopes that we have available to us today. And they were found in the most basic of astronomical images available to us. So it's prior to the year 2000. Around the early 2000s, we then had the advent of digital surveys, digital sky surveys. And one of those was called the Sloan Digital Sky Survey. And when I say digital sky survey, what I mean is that there's an automated telescope that scans large swaths of the sky many, many, many times. And by doing that process over and over again, it essentially allows us to find fainter and fainter objects. So the Sloan Digital Sky Survey is a telescope that's located in Apache Point in New Mexico. And it was very helpful in finding many, many new satellite galaxies in the early 2000s, between the year 2000 and 2010. It was so good at helping us find satellite galaxies that between that decade, 2000 and 2010, the number of then known satellite galaxies doubled from about 10 all the way up to just over 20. Since then, there have also been further technological advancements and better telescopes that have been invented. One of those that's helped us find even more satellite galaxies is called the Dark Energy Survey, or the Dark Energy Camera. This survey similarly is a digital sky survey that again has scanned quite a large region of the sky. And in particular, it's focused a lot on the region of the sky around the Magellanic Clouds themselves, which is quite interesting for a reason that I'll get to at the very end of my talk. But the Dark Energy Survey also helped us find so many new satellite galaxies that even in the last 10 years, again, the number of satellite galaxies known to exist around the Milky Way doubled yet again. So really in the last 20 years, this discovery space has really, really increased. So much so that even this figure that I'm showing you, which I made for my PhD dissertation in 2019, is already a little bit out of date, in that it's showing you that we knew of about 52 satellite galaxies at that point in time, and even a handful more have actually been found even since then, and are currently being studied by astronomers all over the world to really confirm if they are satellite galaxies following that definition that I provided just a little while ago. So we know of approximately 55 to 60 satellite galaxies to be orbiting around our own Milky Way. I've told you there's also a system of satellite galaxies orbiting around the Andromeda galaxy, our neighboring massive spiral galaxy. And in general, we think this is a very common phenomena in that many satellites are found out in the universe around other galaxies as well. So why are these satellite galaxies important? So I'll give you three basic reasons why we're interested in studying them, and I'll link the last one very closely to the work that I do. So the first most basic reason why these satellite galaxies are very helpful is that many of the most recently discovered satellites, the faintest of the satellite galaxies we know to be orbiting around the Milky Way, which we like to call ultra-faint dwarf galaxies, simply because they are very, very, very faint. At most, they weigh something like 100,000 times the mass of the sun, which might sound large, but compared to the mass of our own Milky Way galaxy, which is about 1 trillion times the mass of the sun, they're quite small. So these galaxies appear to have formed their stars in the first 1 billion years after the Big Bang, and therefore they act as windows into the early universe. So this is a timeline that I'm showing that was created to show what the James Webb Space Telescope will be able to tell us, or a little bit of what the James Webb Space Telescope will be able to tell us once it launches. But essentially, these ultra-faint dwarf galaxies are so old that they can really act as probes into the really early universe and the conditions of the early universe that we haven't really been able to directly observe today. So I won't talk about this specific property of these ultra-faint dwarf galaxies in more detail in this talk, but certainly it's a very active field of study that astronomers are working on today. Another reason why these satellite galaxies are very important is that they act as the building blocks of galaxies, or at least one of the building blocks of galaxies. So just like plants and trees need water to grow, these satellite galaxies are really crucial to the growth of galaxies like our own Milky Way. So going back to this picture that I was showing in my title slide, what you're looking at here is an artist's depiction of a galaxy like our own Milky Way, a spiral galaxy here. And what you're seeing around it is a satellite galaxy whose body is represented by this orange sphere that's in the process of orbiting around its host galaxy. And it's getting so close to that host galaxy that its stars are quite literally being stripped away from the main body of that satellite galaxy. So that's what you see in these ribbons of stars, which we often refer to as stellar streams. And eventually what will happen is that this satellite galaxy will completely merge into the host galaxy that it's orbiting around. And it's through multiple of these processes that these satellite galaxies help to build up the mass and the size of the galaxies that they're orbiting around, which in this case I'll call host galaxies. So when we look out into the universe, we see this process of galaxies merging together quite often. And so here I'm just showing a gallery of different stages of pairs of galaxies while they're in the process of merging. Where on the top left, you see galaxies that just look to be close together on the sky. And then they get closer and closer. And eventually you see pairs of galaxies that even look like they're coincident in that they're overlapping with each other, to the point where eventually galaxies merge together and they become one new galaxy. So we see this happening in action, and this is also very relevant to what I'm saying in terms of why satellite galaxies are important, because they contribute to the growth of galaxies like our own Milky Way. And when we look to simulations, we can actually model this process in very high detail. And so I'll show you what we think happens over many billions of years as these satellite galaxies orbiting around galaxies like our own Milky Way and eventually are completely encompassed by their host galaxies. So this is a video of a simulation. So this is all simulated data. And you'll see a time counter in the bottom left, which is telling you the age of the universe. So we're not starting quite at the Big Bang. We're starting quite a bit away from the Big Bang at about 7 billion years, which is about 6-ish billion years prior to today. So it'll count all the way up until the age of the universe now. So let's see that happen. And what you'll notice is that some satellite galaxies, which are these small balls of light, like the one you see that came in from the bottom, and there's smaller ones coming in from all different directions. They enter the vicinity of the host galaxy. Sometimes they pass around it once and they start to have some of their stars shred apart. They pass around it multiple times. But in the process of this happening, some of them eventually just disappear into the host galaxy and are completely encompassed by it, therefore fueling the growth of galaxies like our own Milky Way. So we're approaching almost present day now, where you see fewer of these satellite galaxies coming into the host galaxy's gravitational field. But this is the basic process by which these satellite galaxies are crucial to the buildup of galaxies like our own Milky Way. The third reason these satellite galaxies are very important are that the satellite galaxies themselves, as well as the remnants that they leave behind, help us learn about their host galaxies. So just like in the movie, if we pause it at any given snapshot, we would see potentially a satellite galaxy that's no longer completely intact, but rather its stars have been shred apart, just like in this artist's illustration of a satellite galaxy spiraling into its host galaxy, leaving behind these stellar streams. So these stellar streams are one example of what I mean when I say the remnant of a satellite galaxy. And these pieces of information, when you add them all together, are very useful in helping us understand the gravitational field and the properties of this central host galaxy that the satellites are orbiting around. So let's look in a little bit more detail at the anatomy of galaxies like our Milky Way, which is a spiral galaxy. So if you were to look at a galaxy like the Milky Way from above, you would see this central bar and the spiral arms. And if you look at it from the side, you can see a few more features, which are this disk of stars shown here, and on the edge-on view, it's shown here. It looks like a flat pancake around the central bulge of stars. And for our Milky Way, our sun and the solar system are located in one of the spiral arms along the disk of the Milky Way. And again, this is an artist's depiction of what we think the Milky Way looks like, simply because we can't see our own galaxy in its entirety just because we're inside of it. And from that vantage point, we can't see the very far sides of the galaxy. So these are some of the main components of the Milky Way. There's the bulge, the disk, but one thing that I'm not showing that is very important, and especially in the context of satellite galaxies and how they can be useful in understanding their host galaxies, is the dark matter halo that we think galaxies like our own Milky Way reside within. So to give you a sense of what that looks like, again, in the center, we have a spiral galaxy like the Milky Way, and I very crudely here drawn on a dark matter halo. This is not exactly to scale, because to make it to scale, you would barely be able to see this central galactic disk in the center. But to give you an idea of what the real ratio of those two things should be, the extent of dark matter halos for galaxies around those like our Milky Way, the dark matter halo's radius is about 20 times larger than that of the central galactic disk, like what I'm showing here. And the dark matter halo is also where we think about 85% of the entire galaxy's mass resides. So rather than these luminous regions in the center where we see these nice spiral arms, it's actually the large reservoirs of this invisible dark matter in the outskirts of these galaxies where we think most of that mass lives. And the reason why we think that not only dark matter exists, or one of the reasons why that we think dark matter exists and how we can observe its effect on the luminous baryons that we can observe, is thanks to Vera Rubin, who looked at these spiral-like galaxies like the one shown down here. And what she did was she mapped the rotation speed of stars from the center of the galaxy all the way out to the most luminous part of the galaxy, or rather the least luminous part of the galaxy, or the edge of the visible part of the galaxy. So if you look at the rotation speed of stars in the central regions versus the outer regions, they rotate in the same sense of a ceiling fan or a pinwheel. Those at the center are moving the fastest, and as you go to the outer regions of the galaxy, those stars move a little bit slower. So in general, you would expect to see something like this, where as you go further out from the central regions of this galaxy, the rotation speed goes up, but then as soon as you're away from the stars of this galaxy, the speed of those stars you would expect to decline very rapidly. And instead, what Vera Rubin observed is that as you go further away from the center of the spiral galaxies, the rotation speed of the stars rise, and then they actually stay pretty constant, even after you've left this most luminous region of the galactic disk around these galaxies. So that was quite puzzling in that, in regions out here, there aren't very many stars. So how could the speeds be so high? What mass is contributing to that? And essentially this gap between the observations and expectations are one of the ways in which people like Vera Rubin helped us realize that galaxies must have some invisible massive matter in the outskirts that accounts for this increased rotation speed that is seen all the way out to very far distances. So dark matter is very crucial just to the anatomy and understanding of galaxies like our own Milky Way. And satellite galaxies are therefore very helpful in trying to understand the properties of these dark matter halos because they act as tracers of this dark matter. So in the absence of being able to actually view this dark matter directly, these satellite galaxies still follow the gravity associated with that dark matter and therefore help us trace out where that matter is, even though we can't see it. So what I'm showing in this movie are some predictions that I've come up with for the orbits of satellite galaxies around our Milky Way. So what you're seeing is that, let me start it from the beginning. So I'm starting at 3.5 billion years ago. So each of the white points is telling you the position of that satellite galaxy, what we think it was at least 3.5 billion years ago. And as it moves forward in time, you'll see these lines being traced out, which is what the predicted orbital trajectory we think those satellite galaxies have followed to arrive at their positions today. So I'll let that play. And what I've just depicted in the center here is the bulge in the disk of the Milky Way. And this faint yellow sphere is meant to exemplify the dark matter halo of the Milky Way, which I've drawn as a sphere here, but we don't actually know whether it is a spherical shape or not. And that's another very active area of research today. And so by looking at these orbital histories for these satellite galaxies, which you can see have a broad diversity of shapes, they altogether help us understand what the mass of this dark matter halo is, again, because we can't see it directly. They can also help us understand what is the shape of this dark matter halo. Is it really a sphere? Does it have more of an oblong shape? Is it something totally irregular that is not a normal shape we think about on a day-to-day basis? And so that's the way in which these satellite galaxies are very useful in helping us understand the gravity of the field that they're orbiting within. And as you've probably picked up on by now, these orbital histories are a few billion years. So we can't quite study them by just looking out into the universe and tracking the motions of these satellites directly. But we have to use models and predictions to come up with the full orbital trajectories of these satellite galaxies over time. So what I'd like to talk about for the remainder of my talk is how do astronomers use observations and simulations to study these satellite galaxies and their host galaxies. So in the first part, I'll focus just on the observations. So what's necessary to come up with the orbital trajectories like the one I just showed you in that video are a few different moving parts. So I just wanna briefly highlight what that looks like. So if we're an observer that's looking at a star, let's say in one of these satellite galaxies orbiting around the Milky Way, we might know the distance to that star by having measured the relative brightness of that star, with which we can then deduce a distance. If you also measure the spectrum of a star, which measures the radiation emitted by that star, you also can derive the motion of that star in the direction towards and away from you, which we refer to as a line of sight velocity. So essentially with these two pieces of information, you know how far away that star is or how far away that galaxy is if you're looking at a star in a galaxy. And you also know how it's moving towards and away from you, given that our vantage point is here on the Earth. If you have the additional ability to track the motion of that star over time, so if you take a picture of that star now with a telescope, and then you take another picture of it later, you can then derive something that's called a proper motion. And what that essentially means is if you take the photographs of this star and you track how much it's moved in those two pictures over time, that's essentially what we mean by proper motion. It's measuring the change in angle across the sky, where by angle, it's just a set of coordinate systems that astronomers like to use. But really it's just how is that object moving across the plane of the sky, just like when we look up at airplanes. So when you have these pieces of information, you can then figure out how that galaxy or how that star is moving completely across the plane of the sky. And altogether, what this really means is that we know the full three-dimensional motion of that star, with which we can then try to build an orbital history for that satellite galaxy. So that's a lot of pieces of information. Let me show a more realistic example of what it looks like to measure the proper motion of stars in a galaxy. So the example I'll give is measuring the proper motion of stars in the Andromeda galaxy. So again, the Andromeda galaxy is the Milky Way's sort of twin galaxy. It's the most massive nearby spiral. And I'll show this movie where we'll zoom in on this blue field of stars, which may not look like they're stars that are associated with the Andromeda Galaxy, but I do assure you they are. Even stars away from this main body of the stellar disk are truly associated with the Andromeda Galaxy. And we'll see this movie change as a function of time. And so you'll see the stars in that field drifting with respect to background objects. And in this case, for the reference point, we use very, very, very distant background galaxies, which essentially appear to not move across the sky so that we can trace that relative motion. So let's take a look at what that looks like. So zoom into this field. The brightest white points are the stars in the Andromeda Galaxy, and you see them starting to shift with respect to more stationary background galaxies like the ones up here. Okay, now if you noticed, the timer in the bottom right started at the year 2012, and it counted all the way up to the year 26,112. And that reason is because if you want to actually be able to observe this in the way that I just showed you in this video, where on your screens at home, you can see that natural drift of the stars in Andromeda compared to the galaxies in the background, you need to fast forward time by that much, meaning that these motions are extremely, extremely small. So it's really a feat that we can actually measure these small, small proper motions with telescopes like the Hubble Space Telescope and tease out this extremely minuscule measurement with which we can do a lot of really interesting science. And I like to give the analogy that measuring the proper motion of a galaxy at the distance of the Andromeda Galaxy is equivalent to watching human hair grow at the distance of the moon. So if you had a friend staying on the moon and you had no telescope to observe them with, it's like picking out how fast the hairs on their head are growing. So it's really, really a small, small measurement. But it gives us a whole new parameter space with which we can study the orbital histories of these satellite galaxies and understand their evolution and how they contribute to the larger galactic environments that they live in. So if we go back to the schematic that I was showing early in my talk of the local group, those proper motions are essentially the key to being able to derive the orbital histories of these satellites, some of which I've shown here as colorful examples. So essentially those proper motions, as well as that velocity information and knowing the distance to these galaxies, gives us the full three-dimensional sense of how those satellites are moving, with which we can then understand their orbits. So that's where observations are helpful, in that they can help us track these very minuscule motions. And even though these full orbits, like the one I'm showing here, take many billions of years, that very tiny motion gives us the input to then be able to derive these motions over many billions of years. Okay, now the second part of my question was, how do we use not only observations, but also simulations to study satellite galaxies and their host galaxies? So here I'm showing an animated projection of the dark matter density distribution across a cosmological simulation. That's a lot of different terms. So you may have heard of large scale structures referred to as the cosmic web. So what I mean by this cosmic web is this filamentary structure where you see these brighter regions that tend to be in higher density than, for example, the darkest regions here, which we typically refer to as voids, where there's not a whole lot of matter, either in the form of dark matter or luminous matter. But the important part is that in this cosmic web, at the nodes of these filaments, where you do see these brightest pink regions, that's where we see massive galaxy clusters that contain many thousands of galaxies. That's where they form. And in some of the smaller, less bright pink regions, like some of the ones out here, that's where you would find galaxy groups like our own local group. So a cosmological simulation essentially reproduces a large chunk of a mock universe inside of a computer. And with these types of simulations, we can answer many questions that aren't attainable just with observations alone. And part of that being that observations can't really give us the full time evolution of the formation and evolution of galaxies like satellite galaxies and the Milky Way like galaxies they're orbiting around. And so these cosmological simulations essentially reproduce many hundreds of thousands of galaxies with a whole array of different properties, just like the properties of galaxies that we see out in the universe, with which we can then sort of fast forward or rewind time and understand the different processes and stages of galaxy formation and evolution. Oh, and here's a movie of this playing over time. Okay, so these cosmological simulations contain many different moving parts. And so to give you a basic idea of what's necessary to build a cosmological simulation, I like to describe it as a recipe and to break it down into its component parts. So first, when you have a recipe, of course, you need your ingredients. And so to build a cosmological simulation, you need a set of equations that generally describe the physics of the growth of the universe between the Big Bang and today, which are a complex set of equations, but if you know something about them, you can use them as your base model. You also need an efficient code to actually implement the model. So a lot of what astronomers do on a day-to-day basis is computer programming. And so you need an efficient set of code that can run this very sophisticated simulation. And I'll tell you quite how long that simulation takes and why your code does need to be sophisticated in order to handle it in just a couple seconds. You also need to decide on the number of particles and your resolution and the size of the simulation. And what that really means is you need to decide whether you're just trying to simulate a singular galaxy and its formation and evolution, or on this cosmological type of scale that I'm talking about, if you want to simulate many thousands of galaxies. So you essentially need to pick your poison in terms of, are you trying to represent just a very, very small snippet of what we see in the universe, or a very, very large chunk of it? Next, you have your cooking tools. In this case, we're talking about supercomputers, which you can think of as thousands of desktops or laptops like the one you're probably looking at us on, all added together. So harnessing all of that power in one. And then you need some directions. And so in this case, that includes things like the physics of galaxy formation. What is our understanding of how stars form? How do galaxies merge over time? How do black holes contribute to galaxy evolution? A whole slew of questions that we have some basic answers to thanks to observations, and also other types of simulations. And so we put in all that we know about the physics of these different processes all together so that we can make sure they're really all incorporated. And then you have to wait while your recipe or while your meal is cooking. In this case, our supercomputers have to run for a simulated 13.8 billion years, or the age of the universe, to go from the Big Bang to the galaxies that we see today. And then finally, your meal is in the form of thousands of gigabytes of simulated galaxies and their surroundings that generally match the properties of galaxies we observe in the universe. So those are the very, very, very watered down basics of what goes into these cosmological simulations. They take many, many tens of people to work on each of these component parts to put them together, and many years to put together. And it's not just one supercomputer that are typically used in cosmological simulations of this scale, but it's actually a handful of supercomputers all across the world. So I'm going to show you a movie of one particular cosmological simulation that I've used in my work, which is called the Illustrious Suite of Simulations. And you'll see very briefly two boxes on the screen. On the left side, you'll see the dark matter and the evolution of dark matter in this simulation over time. Because as I've told you a few times now, we think that galaxies reside within these dark matter halos. And so understanding the formation and the structure of dark matter essentially also helps us learn about the galaxies that will reside within that dark matter. And the right side is going to show you the gas in galaxies, which is primarily hydrogen. But you'll notice that there'll be very many similarities between the two different boxes, as they're going to count simultaneously on the same time scale. And there'll also be some differences. So let's take a look at what that looks like. So we're counting from the Big Bang up again to today. So the left side again is showing you the dark matter density of the entire simulation. So remember, it's at the nodes of these filaments where large groups of galaxies are forming. So this is a very sort of zoomed out view of the simulation. And on the right side, you'll start to see that there is some similar structure to the left side. And you start to see these mini explosions, and those are supernovae going off, and these massive stars ending their lives and expelling gas out into different areas of the universe around them. And it's that gas that will then be used to form stars in either the same or other galaxies. But overall, you're seeing that the right side has a bit more of a diffuse structure, and that the gas spreads out a bit more. And the dark matter on the left is a bit more concentrated into these very, very bright regions, and then these large sort of void regions that don't really have much matter in them, either luminous or dark. Okay, so we're approaching approximately today in the simulations. And so remember, what you're seeing is that in these very dense pink regions on the left, there's thousands of galaxies forming there. So in this entire simulation, there's tens of thousands of galaxies that are being formed. So here are some of the main people who worked on the Illustrious simulation. You can see some of the funding agencies and the institutions that they were members of. And this Illustrious Suite of Simulations was run on over 8,000 computer cores and took 19 million CPU hours. And so it's essentially like your laptop computer running for 2,000 years to go all the way from the Big Bang in the simulation to what we observe today. So it's quite a feat that we can reproduce these mock universes in supercomputers. So let's take a look at what some of the data products that come out of these types of simulations, and particularly how I use these types of cosmological simulations to answer questions about satellite galaxies and the host galaxies that they orbit around. So what I do is I look in these simulations and I find mass analogs of the Milky Way. So the Milky Way is about 1,000,000,000,000 times the mass of the sun. So I roughly look for other galaxies that are also about 1,000,000,000,000 times the mass of the sun. So here are some examples of the galaxies from the simulation. So these are not real images of telescopes of galaxies. They are simulated galaxies, though they might look like they're real telescope images. Um, and once I find a few hundred of these mass analogs of the Milky Way, I then go and look for the satellite galaxies orbiting around them. So in particular, in these simulations, I was focusing on the most massive satellite galaxies, similar to the Large Magellanic Cloud that we know is orbiting around the Milky Way. And again, to remind you what I mean by a massive satellite, I'm talking about satellite galaxies that are about 10% the mass of their host galaxies. And so I've just circled some examples of what this looks like, again, in these images. So in the images, they look quite faint, but nevertheless, we are able to identify these massive satellite galaxies. And so when we do that, we find, again, something like 500 systems of a Milky Way-like galaxy and a massive satellite or multiple massive satellites orbiting around that Milky Way. So as a summary of what all of these tools together give us is that the observations tell us the precise 3D motions of these satellite galaxies, with which we can then build the orbits of these satellite galaxies over the last few billion years. And then the simulations help us with statistics in that the simulations provide us with hundreds of Milky Way-like galaxies and the properties of the satellite galaxies orbiting around those Milky Way-like galaxies. So we essentially get hundreds of replicas with slightly different properties of our own Milky Way and the satellites around our Milky Way. And so together with both of these sets of information, we can answer some more specific questions about the satellites of the Milky Way, or the satellites in the local group in general, and also questions about our own Milky Way galaxy. So here are some of the things that I've worked on over the course of using these types of tools in the last 6 or 7 years. So one is, what is the frequency of satellites around simulated galaxies like our Milky Way when we look into these big cosmological simulations? And what that can help us answer is, are we missing any satellites? So have we found all of the satellites that we expect to be around a Milky Way-like galaxy? And so far, we found almost about 60 satellite galaxies around the Milky Way. And what these simulations tell us is there actually should be maybe something like 200 satellite galaxies orbiting around the Milky Way. So we still have a way to go in finding, especially these very faint, ultra faint dwarf galaxies that have many of which have just been discovered in the last few years. So hopefully with new telescopes and new technology, we'll be able to bridge that gap between the observations and the simulations. Another question we can answer is the Milky Way and its satellite system common or rare? So if you look at the properties of the satellite systems within the simulations and compare them to the real properties of the Milky Way and its satellites, you can assess how common or rare those properties are. You can also look at the orbital properties of the satellite galaxies, both in the simulations and those that are derived from the observations. And again, figure out whether those are typical. Are the types of orbits that we get normal, or is there something maybe different going on, which might require maybe some additional physics or some other considerations to fully explain? Another question is, what do the current orbital properties of the satellites imply about the properties of the host galaxy? So I gave this as one of the 3 reasons as to why these satellite galaxies are important. And when we can compare the real Milky Way satellite galaxies to the many hundreds or thousands we find in simulations, we can narrow down properties of the Milky Way, such as what is the exact precise mass of the Milky Way and its dark matter halo, given that we can observe that dark matter very directly. So one example of that is some work I did back in graduate school, where we looked at how do you weigh a galaxy, and especially the one you're in. So using these combined set of tools, we can ask the question of what is the exact mass of the Milky Way? Okay, so finally to end, I just want to show you a quick case study of the types of questions, of a more specific case rather, of some of the questions that I've shown here. So what we'll look at is the orbital history of the Triangulum galaxy. So as a quick reminder, if we go back to the schematic again, we have the Andromeda galaxy over here, and Triangulum, or M33, is this galaxy here, which is another spiral. It is a satellite galaxy of the Andromeda galaxy. And just like the Large Magellanic Cloud, Triangulum is the most massive satellite galaxy we know to be orbiting around the Andromeda galaxy. So again, it's roughly 10% the mass of the Andromeda galaxy. So we'll look at the orbital history of Triangulum. So here in this image on the right side, this is real data from a telescope in Hawaii, which did a large survey around the region of both the Andromeda Galaxy, which is now shown here, and the Triangulum Galaxy, which is shown down here. And all I want to point out here is that in this very deep survey of this region, many interesting stellar features were discovered, which are highlighted in these contours. There are all these irregular stream-like features, some of which have been connected to satellite galaxies disrupting, like I've shown you a few times throughout today's talk. And others are interesting, like this debris down here around M33, which seems to be somewhat irregular shaped stellar debris in the outskirts around the Triangulum Galaxy. And so the question we asked a few years ago is, where does this extended stellar debris around M33 come from? And how can we explain it? So prior to the time that I was in graduate school, and actually prior to having a proper motion measurement for both Andromeda and Triangulum, which are the two pieces of information that are crucial to being able to directly come up with an orbital history of Triangulum, the then proposed picture was that Triangulum must have gotten close to the Andromeda Galaxy, its host galaxy, in the last 3 billion years or so, and close enough to it that the gravity of Andromeda was so strong that it started to pull away some of the stars in the main body of Triangulum. And that's how you can explain that stellar debris that was discovered in 2009. While I was in graduate school, by that point, the proper motion of Triangulum and Andromeda, which is what gives you that full three-dimensional knowledge of how these two galaxies are moving relative to each other, became available. And so we were able to more rigorously ask, if we predict what the orbital history of Triangulum was, does it match this original picture, which could then potentially explain that stellar debris? And what we found was no. The orbits that we were able to find were actually ones where Triangulum is only getting to the position that it is today for the first time, which is this distance shown here, meaning that it didn't have a recent interaction with its host galaxy Andromeda, and therefore that can't be the explanation for why we see that stellar debris in the outskirts of Triangulum. So then we're left with an open can of worms in that if there's this orbit that doesn't seem to show a recent interaction between these two galaxies, then what could it be? Where does that extended stellar debris around Triangulum come from? And so another project that I followed up with, and one potential hypothesis, and I should say that this is not the only potential explanation, but the one that I favor, is that Triangulum itself might also host a population of its own satellite galaxies that through interactions of their own might give rise to that stellar debris we see around Triangulum. So we're talking about a set of satellites orbiting around another satellite galaxy, which is then orbiting around, in this case, the Andromeda Galaxy. So we're talking about a satellites of satellites hierarchy here, which is quite exciting and a thing that we're starting to see in multiple galaxy systems now. About a handful of galaxy systems have a satellite and then satellites around them. So it's an exciting new area that we can approach questions like this with. And I will end there. So hopefully I've explained to you why satellite galaxies are interesting and a fun thing to be studying at the moment, and why this area is so actively increasing, and why I've had so much fun working here. So I'll take any questions now.